educators, welcome to Learn Extra Live. Today we are doing grade 12 physical science and John is here with us. Hello John, how are you?
Hi Katlego, great to be with you guys, and
Awesome.
you know that today we are doing paper one.
Paper one revision is very important.
You know what? Guys are writing paper one on Thursday.
Sure.
So the countdown has begun.
Yeah.
And the great news is that we've been going since 9 o'clock this morning. I know a lot of guys out there were doing accounting this morning. But don't worry, we're going to repeat everything that we've done this morning tomorrow. Awesome. So for guys that were writing today, you can watch tomorrow. Guys that were not writing today, well, you might be writing tomorrow. Hope you've watched everything. And it's also on later today.
That's awesome. And it's always nice to watch it twice so that, you know, if you missed something or a question that you wanted to hear, then you can just watch it all over again.
And talking about watching something twice, Kat, you know what? Lots of learners have said to us they'd love to be able to see a repeat of the live show. And so what we've done is we've put together special procedures so that at 10:30 tonight, this show will be repeated. So if you're watching at 10:30 at the moment, you didn't see the afternoon show, guys, we're with you still, but it's obviously still a repeat.
Yeah, it's still a repeat, but hey, we're with you 10:30 people and we're with you 3:30 people.
Absolutely. And we've got some great surprises and some great new additions to exam school.
Yeah.
So we'll chat about that a little later, but I think you've got something more to say. I've got to get to the board.
You can get to the board, John. Thank you, John.
Thanks, Katlego.
Cheers. See you just now.
Yeah.
So, of course, you guys know exactly where to join us by now. Our Facebook page, facebook.com/learnextra, as well as our Twitter handle, which is @learnextra. And John will be talking to you about a new addition, which is our Mix It. So John will chat to you about that just now. But before he does, I want to remind you that today we want to do as many of your questions as we possibly can. So please send through your questions on our Facebook page, on our Twitter, wherever you find a place to send, just send them through, guys, because John is ready and steady today to take anything that you need to take. And of course, because you guys are writing on Thursday, you are first on our list right now, grade 12, because we want you to do the best that you can possibly do. Is that not so, John?
Absolutely, Katlego, absolutely. And we're really ready for all your questions. We've even scheduled another show tomorrow, and I think Tracy will be here to deal with your questions. So if we don't get you your questions today, if I'm not able to answer your questions today, we'll make sure they're included in tomorrow's show.
Of course, and all week is science.
It's science all the way through. On Thursday even, I know the guys might be feeling a little tired, so we've dedicated Thursday for grade 11s, but it's basic chemistry. So if you're struggling, grade 12s on some basic chemistry, after your exam on Thursday, join us on the live show as well. We'll be going through some basic stuff that will be applicable to you. Then Friday is paper 2, Saturday paper 2, Sunday paper 2, and we're going to make sure that you're ready for physical science.
That's fantastic. I know you guys are going to do really, really well. So I'm hoping that you guys will also send through some of those great results because I'm looking forward to seeing them.
Absolutely. We're ready to party already.
We're ready to party already.
And we're getting ready for the 21st. Eh?
Yes, we are.
Do you know about the 21st?
Yes, I do know about our 21st party. I actually want to tell you what number we're on as we speak. Right now, our likes have reached, let me just get to it, 21.
Yeah.
638.
Brilliant, eh? That's amazing.
Absolutely amazing. In 2 days, John, we've had more than 700 likes on the page.
That's brilliant. Absolutely brilliant. And we want to grow it. Let's see how many more we can get. And remember, you can send your entries into that 21st party. We wanted to get 21 mindsetters in the studio here. We're going to have an awesome time. Great time just to relax. I know that there are 1 or 2 exams after the 21st, but they're not that important. Well, they are all the exams important. But you know what? You can make a 2-hour jam session and a party celebration on the 21st. But
that would be
you know what? I'm talking too much about the fun things.
We should go on to the science.
Let's get on to the science. Thanks, Kat. Okay, guys, we're going to start. What do you expect in your paper? What do you expect? The first question you're going to look at when you open your paper is going to be a one-word answer question. In your reading time, make sure you read through as much of the multiple choice and the one-word questions. Remember, you don't have to answer in the order, question 1 through to 7 or 12 or whatever the number it is in the paper. You can start anywhere. What I suggest that you do is in your reading time, you read carefully these one-word questions, and you don't have to answer them straight away. There's usually a special answer sheet that you can answer them on. Just read the exam instructions very carefully and don't make a mistake. Make sure you answer them in the right place. Number your questions extremely well. The reason what I prefer to do and what I say to many of my learners is that choose the question that you like best. Now, you might like the Doppler effect question, or you might like the circuit diagram question the best. Do that one first. After you've read the one-word answer questions and the multiple choice, that's combining all your knowledge. And so it gets time to warm up. Once you've warmed up and you're feeling a bit more relaxed, go back to these one-word answer and multiple choice questions. But for today, we're doing some revision. So let's do some revision about all of physics, not focusing on one particular topic. Let's see if we can get these right. These are taken from the February-March 2012 paper, and let's just quickly do some revision of these particular questions. Okay, so one word, you usually have to answer them in your answer book, and we'll go through them. The type of energy an object has due to its motion. Now, guys, you know this. This is basic stuff. If you can see a question like that, you've got the answer book, you write it down straight away. Don't even think about it. We know that this is kinetic energy. Okay? Kinetic energy. Write out the word in full. Don't be silly and write EK only. You can write kinetic EK or capital K as the symbol, and remember the formula for it. So because we're just doing revision, I'm going to remind you about the formula because you might get this in a longer question, and it's on the data sheet. It's half mv squared. So guys, when you do a past paper, doesn't matter which one it is, might be the 2008 all the way through to the 2012 paper, think and revise your concepts and your notes. When we're thinking of energy, what should we be thinking? Conservation of energy. Remember, energy can't be created or destroyed. Mechanical energy is the product, the sum of potential energy and kinetic energy. Now, they're not going to ask you this question in tomorrow's or Thursday's exam, but they could ask you potential energy. So make sure you understand that potential energy is the energy due to an object's position. Okay, we've revised energy. Let's move on. The next question, the phenomenon which occurs when two light waves meet at a given point. Now, if you've got two waves, doesn't matter if they're light waves, water waves, sound waves, they meet and they're in the same point, in the same medium. Well, there's going to be something that's going to happen. We call that interference. In this case, we're not sure whether it's constructive or destructive interference, but we'll revise that. So we could say that this is interference. Just remember, there are two types. When we get a wave like that and a wave like that, and I'm going to just select that one and hope that we can, no, it's not working. I'll just have to do it again. If we take one of those waves, let's just erase one of them, just so that we've got it as a separate item. Write another one now, pink one, and if I put this one on top of that one, what's going to happen? We're going to get a bigger one. So if they're in the same space and they're on top of each other, we're going to get not just a pink one and a green one, we're going to get a bigger one. It's got double the amplitude. That's if they interfere constructively. Okay? Constructive interference, when the two waves meet at the same point, they're both wanting to go up. The principle that we're using here is the principle of superposition. Make sure you understand that principle. What about destructive interference? What happens there is I'm just going to try and illustrate it again, and this time I'm going to just separate these and do a fancy trick here. Let's get rid of that one quickly. Let's move them around. So we now say that those two waves are going to meet. You can see that they're roughly the same amplitude. So what happens when they meet? That's destructive interference. And the end result is that they cancel each other out. Only for a moment, because after a while, look what happens. And this is important for both constructive and destructive interference. That one's going to move that way, and the green one will carry on moving in the direction that it was. So we're going to find that wave continues moving that way, and that wave continues moving that way through the medium. Right, guys, so make sure you've revised the very important property of waves, which is interference. Now, the reason that it's very important for light is because we recognize that light can either be considered a particle or have a particle nature or a wave nature. And interference pattern from a single slit or from a double slit gives us evidence that light has wave-like properties. Whereas the photoelectric effect, which we'll come and talk about, I think, a little later, we will say that's evidence for the particle nature and the fact that light can be represented as packets of energy called photons. Okay, hope that's revised that little section, and we're moving on. Now we get to an electricity question, one of my favorite sections, and this, guys, is really straightforward because it's grade 11 work. Now, I know that you might not have spent as much time on it. Hopefully, you've spent spring school where we did a lot of electricity, and since then, you've had an opportunity to go over some more electricity. Guys, it's an important section. Out of the 150 marks in the paper, you could get as many as 40 marks on electricity and electrodynamics, up to 55 marks out of that. That's more than a third. So it's not a section that you can waste your time on. Make sure you've mastered this. So let's get to the question. The unit, now be careful, the unit of measurement of electrical resistance. What is that? Now, remember, resistance has a symbol R, but it has a unit that is called ohm. And the symbol is that. So the unit of measurement is the ohm. And we need to make sure that that's the SI unit. We will be very particular about using SI units in our physics paper and in our chemistry paper. So please make sure that when you're dealing with electricity, one thing, particularly electrostatics, that you convert your units to SI units. That means you must be working in coulombs, you must be working in meters. You must make sure that you're working in amps and volts and not milliamps and milliohms or anything else. Make sure you've got the right units. Make sure that you also don't get confused between the symbol of the quantity, like R for resistance and ohm for the measurement of units. One way that you can tell the difference is that you never have a formula with that in it. And the other thing, you will always have in an answer the number with units. Extremely important point that you need to take note of for all your physics long questions. When you give an answer, make sure you have the right unit with your answer. If it's a vector quantity, that needs to have direction as well. Remember the vector quantities being force, velocity, acceleration, and the derivatives of those, momentum, and even something like electric field strength. But make sure you just revise those as well. Right, we're going on to the next two questions in this paper, and we come to question number 4. It says, the principle, let's just pick a color, the principle, very important, on which electric generators function. Now, that means what makes an electric generator work? What was the science principle behind it? Now, remember what an electric generator does. If we provide a turning coil in a magnetic field or a moving magnet in a coil, then we will produce an EMF. So it's movement, mechanical energy, rotational mechanical energy, into electrical energy. That's the principle on the generator. So how do we get that? How do we make electricity? What's the principle? Well, here it is. It's related to that most wonderful physicist who did some great discoveries, and he's a model of real perseverance and study, Michael Faraday. Michael Faraday was came from a very poor family. He wasn't even able to go to school. He taught himself to read and write. At the age of about 15, he became an apprentice to a bookbinder. But he was one of the most amazing people that came from the working class, poor environment, and he made physics accessible to everyone. At that stage, in that history, in the 1700s, people that were the elite, the nobility, were the scientists. Michael Faraday opened up science for you and me. So we need to thank him for it. So the principle of that Michael Faraday found and represented here is called the principle of electromagnetic induction. Because what he was saying is you use movement of a magnet in a coil or a coil in a magnetic field to produce electricity. It was an absolute breakthrough. It was a miracle discovery because out of that, we're able to produce electricity, and we don't have to depend on electrochemical cells, which I know that you study in paper 2. But let's move on. So the next one, the type of line spectrum. Now, again, very important. We're dealing with spectra here. Observed when electrons in an atom move from the excited state to the ground state. So let's just say that we've got an atom here, and that's the ground state, and that's the excited state. What we're recognizing, we've got an electron that normally sits in the ground state, and it is in the higher energy state, and it drops down because it can't stay there. It's unstable. What happens to it? It releases a photon of energy. So it releases light of a specific frequency, a specific color. So there's one color. And so when we look at the spectrum, what are we going to see? We're going to see light of that color. So instead of seeing red, orange, yellow, green, blue, indigo, violet, the whole spectrum, we're only going to see certain lines where the electrons have emitted photons of a particular frequency. So this is known as the line emission spectrum. Line emission spectrum. So the type of light, it's a line emission. It's not an absorption. It's giving out energy. In this case, hot gas is excited. That's what gets the electrons into the higher state. With absorption spectra, remember what happens there. It's cool gas, light shone through the cool gas, and the electrons absorb energy, and you get black lines in the place. Kat, we've almost done question 1, but are there any questions?
There actually are.
Okay, throw them at me.
I don't want to throw them at you right now. Do you know why? Because I don't know if they're relevant to what you're doing, but I'm going to read you one.
Okay,
that
that's fine.
I think maybe. Sfeso says, clarify when exactly we use the components of gravity.
Okay, excellent question. Now, it's not what we've done, but it's absolutely fine. We're not holding to one particular topic today. So anything goes, but send your questions. Those things that are bugging you, not sure about. And Sifo, you've asked a brilliant question, and I want to just explain it. Now, very quickly, because we haven't got a lot of time to do this, let's say that that's an object that's sitting on a table, or a ball in space. We recognize whether it's a ball in space or sitting on the table, there is a force downwards, which we call the force of the Earth, or Fg, which is sometimes called weight, which is equal to the mass times the acceleration due to gravity. Be very clear about this. Gravity always acts directly downwards. Okay? So Sifo's question is, when do we use components? Well, components are used when we have something that is not able to act directly downwards. In other words, when it's on a slope, when it's on a plane. Now, the force of gravity is still acting directly downwards, but here we've got to think about the fact that we can break this downward force into two parts, known as components. And the one is going to be perpendicular to the surface, and the other is going to be parallel to the surface. And so you need to make sure that you understand how you get those components and recognize that the angle of difference there is the angle of the slope. Okay, just remember, often you're asked to find FG parallel, and I'm just going to put that in. FG parallel is going to be FG times sine of the angle theta, where that angle is the angle of inclination. Okay, that was very quick, but I think it's covered the question.
Yes,
Kat?
it has, definitely. Should we go for an ad break? Yes, let's go for an ad break. I am going to show John all of your questions, guys. There are some great questions that are coming through. Please don't stop sending. If you haven't sent a question, guys, post it on the page right now. Don't wait till the end. And of course, don't wait till last minute, because we are waiting for every question. See you right after the break. Welcome back, Mindsayers. If you have just joined us, we are doing exam school today, and it's physical science. Guys, I know all you science guys are thinking, this is fantastic because we're writing on Thursday, and this is exactly what we needed to know. To help you more, guys, we want you to answer and to send through any questions that you maybe you're unsure, maybe you're like, oh, but then the memorandum says this and I need clarity. There's many questions here that are like, John, please just clarify this for me. And these are awesome because John is going to do exactly that, guys, because that's exactly what we're here for.
Absolutely, Katlego. Yeah. Guys, apart from you posting questions, we've got something really exciting to share with you. Now, today's the first day that we're piloting this. So you're a special group of viewers right now. We've got a platform that we're setting up, and we're wanting to invite you to join us. It's called Curio, and it's found on Mixit. I want to show you, first of all, how to get into it, and we're going to post these instructions on the page for you, on the Facebook page, and it'll come up quite often. But so what we're going to do is we're going to put together every day a whole set of a range of multiple choice questions. So we've done short questions, now we've got some multiple choice questions. Now, these don't necessarily come from exam revision, or they don't come from exam papers, but they're ones that are challenge questions. They're ones that I've thought up in some cases, or I've taken from different sources where I think they're really good questions. So how are you going to get hold of this application? It's a Mixit application, and I want to just take you through very quickly how to get hold of it. Curio is what it's called. What do you need to do? Get onto Mixit, and once you've logged onto Mixit, step one that you're going to do is you're going to go to Add Contacts. You're going to go to Add Contacts manually, and within that manual list, in the text box, write qa.ed.ge. So it's qa.ed.ge, and then what you do is you send an invitation and finish. Go down to the bottom of the page, send an invitation and finish. And this is absolutely free. There's no charge to you. You will get, you'll see just now, an SMS back. We're sorting that out. You won't be charged for it. Go to the apps menu once you've done that, under General Apps, and you look for qa.ed.ge. And then you need to register. It's very simple. You register your name, your mobile number, which is kept totally confidential, and then you will get a confirmation SMS. That confirmation SMS will have a code that allows you to log in. Once you've logged in for the first time, you'll be prompted to put a new password in, and then you can use Curio for assignments. And you go to the homepage on Curio once you're there, and you will be asked assignments, and then you have to put in a code. So today's code is PS for physical science, PSCI 23. So PSCI 23. So we don't get it confused. It's physical science, and today's the 23rd. Got it? Now, if you go into that assignment, and I know I've gone through it quite quickly, but hopefully you'll get it sorted out. We'll put the instructions on the Facebook site for you, and make sure that you can follow through. Then you're going to get a whole range of questions that will really stimulate you and make sure that you're getting them right. What we'll do is we'll check which ones people aren't getting right, and we'll answer those ones in tomorrow's show. But just to give you a taster, I've got one up, and I'm going to go through it. I'm not going to give you the answer. I'm just going to give you the overview of it. Okay, so Curio, get on to Mix It, and let's engage. Let's brush up on our practice. Make sure that we kill multiple choice absolutely all the way through. So here we go. This is a tough one, and it's dealing with momentum. I had somebody earlier sending an email to helpdesk@learnextra.co.za, and they said, please explain momentum. So here's the momentum thing. When you see the word collision, or you think about momentum, you must be thinking about two things: conservation of momentum, and you must be thinking about collisions. The law of conservation of momentum says that the total momentum before in a closed system, it stays the same. So the total momentum in a closed system, an isolated system, remains constant. Any of those wordings are fine. What that means is before a collision, total momentum is equal to the total momentum after the collision, as long as there's no resultant force or external force. So two bodies bouncing into each other and moving apart, moving along together, that is going to be considered conservation of momentum. It's a linear momentum. We're only worried about it in one direction, not two directions. So they have to be head-on collisions. So there are really three types, where one is stationary, one collides, and they move off together. Or one is stationary, one collides, and the one moves off, the other stays behind, or they move at different speeds. And then you get the situation where they move together, and they collide, move apart, or they start together with springs or magnets, and they're released and they move apart. Okay, so those are the type of collision questions you can get asked with momentum. Remember, when we talk about momentum, we define momentum very simply as symbol P for momentum. Don't ask me why it's P, is equal to m times v. So it's the mass times the velocity, and it is a vector. So we need direction. We need to make sure that we take direction is important. Look out for your direction. So when we're doing a vector problem, make sure you assign signs, which is positive, which is negative. Let's get to the question now. So I'm going to read it first. Two trolleys. So we've got two trolleys, A and B, and they move towards each other with a velocity of 6 meters per second. After colliding, the trolleys stick together and continue to move at 2 meters per second in the same direction as A moved before the collision. Which of the following statements is true? Guys, before I even get into discussing the options, and this is a Curio question, remember the code. If you're on Mixit, it's PSCI23, and this happens to be, I think it's question 3 or so on that assessment for today. But let's go through. What are we going to do? The first thing we're going to do is we're going to draw a little diagram. We've got time to do this because they're moving together. We've got trolley A and we've got trolley B. And we are told that they move towards each other, each with the same velocity of 6 meters per second. So there's my diagram, and I'm going to say this one is moving, A is moving to the right, and it's moving at 6 meters per second, and B is moving to the left, and it's also moving at 6 meters per second. And that's before the collision. So I'm drawing my before picture. You know those wonderful adverts that you get for exercise programs, the before and after, not the really ones where people look very healthy and excited before and tired and flattened out after. Yeah. No, they don't usually do that.
Yeah, no, they don't.
They kind of show the overweight and the sluggish before,
and then they show the thin and fit and strong.
Yeah, and happy, smiling.
And happy, smiling.
But I'm not sure it works like that.
I'm also not sure.
Okay, so here's our after picture. So draw the after picture so you can see what it looks like. And what we're going to say is we've got trolley A, still the same trolley, and trolley B, and it hasn't changed, but they stick together. So they're stuck together, and they're moving in the same direction as trolley A did, but they're now moving at a velocity of 2 meters per second to the right. And what we're now asked to do, look at the options. Which of the following statements is true? The mass of trolley A is equal to the mass of trolley B. The mass of trolley A is double the mass of trolley B. The mass of trolley A is half the mass of trolley B, and the mass of trolley A is equal to 3 times the mass of trolley B. Wow, guys, that's quite an option. Now, there are 2 things about multiple choice. Once you've drawn the picture and you've got that clear in your heads, what you've got to do is try and do some working out. I've told you what the principle is. And the principle is the law of conservation of momentum. So if we were to look at the law of conservation of momentum, we would say the sum, sigma, of the momentum before is equal to the sum of the momentum after collision. Now, I'm not going to work it out any further than that. All I'm going to say to you is very carefully assign your direction, and I would suggest to you, make your direction something like this. Direction to the right is positive. Could be negative, doesn't matter, but as long as you put it in, then substitute into that formula and see if you can find a relationship between the mass of trolley A compared to trolley B. Make sure you work it through and check out the answer. If you've got a mobile phone and you're on Mixit, go to the phone and you can select. Once you put in the code, you can see your selection. It will refresh after you do next question. You'll say, refresh it, and you'll see you've selected your answer with a little star. That's your answer. Submit it, and we'll let you know what the results are and make sure that you've got feedback on getting the right answers for each of those. Okay, so don't go away. Have a test of it. Make sure that we get as many opportunities to practice, and you will get your feedback sent to you from that platform. Okay, so I think that covers multiple choice questions.
Yes.
It covers momentum, but there were some short questions that we looked at during the break. I'm sure there might be others that have been added, but let's see. Was there anything on momentum, by the way?
There was nothing on momentum, John.
Okay, that's fine.
But I'll ask you this one by Aki.
Yes.
Aki asks, firstly, what is the difference between EMF and PD?
Okay, very good question. I'm going to go down to a blank page just to get this sorted out. Okay, so when we're looking at a circuit, and I'm going to draw a very simple circuit here, and I'm going to put a switch in it, and I'm going to put a couple of resistors. Doesn't matter. These ones are in series. Okay. Now we're going to say, let's put a voltmeter across this battery of 2 cells. Okay? Now, guys, have a very careful look here. Is there any possibility of current being able to pass through the resistors? And you'll say to me, absolutely not. Look here. We've got the switch is open. So we've got an open switch. No current is going to go through here. So in other words, at this point, there is no work done in the external circuit. No work done external. Now, Kat, I don't know about you, but when I was at school and even at university, people gave you these tests. They were either EQ tests or IQ tests. Yeah, you know those sort of potential testing tests. Yes. Okay, and they come up with a fancy number and say to you, "Oh, yeah, you're in that category, or you're in that category." Yeah, you've done that. Yeah, you remember those. So I like to think about this scenario. When the switch is open, it's just like one of those tests where we're measuring potential.
Oh, okay.
And we're measuring here on this voltmeter the maximum possible outcome. Maximum possible outcome. And we call that EMF. Okay,
Yes.
so we've answered
makes
that part.
sense. Yes. we
Makes
have.
sense. You're following.
I'm following.
Okay, hope the guys out there are following. But now, you know what, guys? I know that there are lots of you that have got lots of potential. You've got brains that are so big, and you've got the ability to succeed. You're going to be the leaders of science, technology, industry, the whole lot. In a couple of years' time, you're going to have the top jobs in the country. And that's what you've got. You've got the potential to succeed. You believe in yourself, you work hard, and, well, you've got the gift to succeed academically.
Of course
and
they do.
that's awesome, hey?
That is great.
But there are a whole lot of you out there that have got that potential, but there's a problem.
You don't use it.
When it comes to something called work,
Yes.
comes to something where you've got to actually do some work. You can't expect next year when you go on to whatever career you go on to, whether it's in a career, in a job, or you go to on-the-job training, or you go to a FET college, or you go to tertiary study, you're going to have to dig and do some hard graft. You're going to have to get your hands dirty and really spend some time putting in the effort. And you know what? That's the problem. When we close the switch, and I'm just going to try and see if I can do this. I'm going to try and do something fancy and hope that it will work. Might not. But there we go. And I want to just see if I can copy that. And now I'm going to pull that down and see if I can paste it. And let's see if we can pull it down. There we go. Now, in this situation, second situation, we haven't got the maximum because at this stage, what we're going to do now is we're going to say, guys, same circuit, different scenario, we're going to close the switch. Now what has to happen? We've got to do work. Why? Because the current needs to pass through the external circuit. It's got to go through the resistors or through light bulbs, and so there is work done in the external circuit. Okay? There's work done in the external circuit. The problem is that if there's work done in the external circuit, and it's the analogy that I've been building up to, you've got maximum potential when there's no work done. When there's work to be done, you know what? There's a problem, and the problem is inside here. The problem is inside the battery, and we call it internal resistance. Because we know that a lot of young teenagers would rather sit on the couch and let everyone else do their work for them than to actually get busy. Okay. Now, we're comparing circuits here to teenagers. Not you guys. I know you're motivated, but you can understand. When there's work to be done, then there comes a bit of internal resistance. Now, the reason for that is that charges have to move from the negative terminal back to the positive terminal. And so inside each of the cells, there's a thing called an internal resistance. What that means is that not all the potential is available for the external circuit. Okay? Some of the potential has to be used up. Some of the energy has to be used up inside the battery. The thing that is being used up outside the battery can't be equal to the EMF anymore, because there's got to be some work done inside the battery. It's kind of, you've got to not just do work as output here, but you've got to do work between your ears as well. There's got to be some hard thinking, hard working. Okay, so this voltmeter now, when the switch is closed, that voltmeter is going to measure something that we call the potential difference external, and some people call this PD. Okay, but it shouldn't just be PD, but it should be PD external. What we're saying, it's the work done in the external circuit. Okay.
So, John, in relation to that, Tesla asks, how do you calculate the EMF of an internal circuit?
Okay, the EMF is just the reading on the voltmeter. So when the circuit is closed, when the switch is open, that will be the EMF. So if we say that we've got 4 1,5 volt cells, okay? So if you could take a little cell and you put the reading on that cell is the EMF. That's what the maximum is.
Okay.
So after a while, the battery goes flat because it's not able to deliver, because it's got more resistance inside. The products that build up, they're waste products that prevent the battery operating efficiently.
That's awesome.
But you know what? What we want to make sure is that all the guys out there, their cells are rejuvenated. So I think they need to have a little moment of a break.
I think
stretch,
so too.
do some exercise, get some oxygen into the brain, and make sure they're ready for the next part.
Thank you, John. Aki, what a great question. Everyone else, please send through some questions. We will be going through more of your questions. So don't leave us, guys. Stay with us. See you right after the break. Welcome back, Mindsetters. Wow, what an awesome show it has been. I've been looking at your posts on the page. It's been so great to see that you guys are so involved. Also, that you are so keen to pass. Someone even said we are getting distinctions, and that's so awesome to hear, guys, because that is all we expect. We expect the best from you guys. Whether your best, whatever your best is, we know that your best will be the greatest possible outcome because they have the greatest possible potential.
Absolutely, that's great. Yeah, thanks, Katlego. That was really great. I hope you've had a stretch. Now, there was a question on the page, just in the break, that I picked up about what's the difference between.
It was, how did we differentiate the definition for Lenz's law?
No, just hold on.
Another one.
It was the previous one about potential and work.
Oh, yes. I have it right here, John. Is work and potential difference the same thing?
Okay, now guys, in my explanation over here, is work and potential the same thing? No, they're not. We need to be very clear about that. I was just saying over here that work is done in the external circuit, but work and potential difference are very closely aligned. Remember the definition of potential difference. It's the work done, so it is the work done between 2 points in moving per unit charge of work between 2 points. So in moving a charge from this point over here to that point over there where the voltmeter is reading, the work done per unit charge is going to be what the potential difference is. But now, guys, if we do, let's say, 30 joules, and it's only 1 coulomb of charge that moves, then that's going to be more work than if we did 30 joules of work and we moved in that same process. We moved, say, let's say, half the number of charges, did the same amount of work, then there'd be a greater potential difference. So you need to recognize it's W divided by Q. Okay, so work and potential difference are related, but they're not the same thing. Okay, the one about Lenz's law, Faraday's law, electromagnetic induction.
That's it.
Okay, so guys, this is grade 11 work. It's very unlikely that you're going to get asked on Lenz's law in the grade 12 exam. The idea of electromagnetic induction, you're going to need to know, because that's related to generators. You could also get asked to write down the formula, which we write down in terms of the principle is called the principle of electromagnetic induction, but the formula of Faraday's law, which is the description of the principle, Faraday's law, which describes the principle, is that the induced EMF is equal to minus the number of turns, delta phi over delta t. And what that is saying is the EMF is directly proportional to the rate of change of magnetic flux. Okay? So make sure that you understand that that's Faraday's law, and that is describing the principle of electromagnetic induction. It is not electromagnetic induction. Lenz's law relates directly to this minus, which simply put says that if we've got a coil over here and we've got a magnet over here, this is for grade 11s, and we have a north pole coming in that way, then what's going to happen is the induced EMF is going to work in such a way so that the magnetic field that's around here is going to oppose the motion of this magnet. In other words, it's going to work in such a way to produce a north pole at this end. In other words, if we use the right-hand rule, we would see that the current would have to go that way around to produce a north pole to try and resist the change in magnetic flux. Okay, I know that's a little bit quick and a little bit complicated, but it's not really required for grade 12, but I've tried to explain the answers as it was asked on the question. I'm going to move on. Please keep on asking your questions. This was earlier. Somebody sent in a mail to the help desk with a photo of a question from their prelim paper. It was from one of the provinces that we haven't done, and I thought it was really nice. It's from the Mpumalanga prelim paper. Let's have a look at it. It's a vertical projectile motion question. So I've paraphrased it a little bit. It tells us the following, that Layla is in a basket of a hot air balloon, and that she's moving downwards at a constant speed of 4.5 meters per second. She's 9 meters above the point where Johnny kicks a ball vertically upwards. Now, in the paper, there you've got the sketch. There's Layla. So that's Layla, and that's Johnny. And what we recognize is there's a difference of 9 meters between her position and where the ball is kicked. So the ball at that point, we'll see now, the ball has an initial speed of 12 meters per second. And he's kicking it directly upwards. So it's vertical speed, the initial speed of 12 meters per second upwards. Right. So the ball, Johnny is standing 80 meters above the ground, and it says we can ignore air friction. So there's the scenario. We've got it. The balloon is moving downwards, and this is constant. So it's not changing. Where the ball starts with 12 meters per second, but we know that it's going to experience an acceleration due to gravity, which is equal to 9.8 meters per second downwards. Let's look at the first question. It says, calculate the maximum height the ball will reach above the ground. Now, I'm going to make a very special note here. The maximum height the ball will reach above the ground. So guys, we need to make sure that in our final answer, whatever we're going to do is the ball's going to go up. It's going to reach a maximum height. We don't know, is it there or is it there? We're not sure at this point. But we must add in that 80 meters. So the maximum height is going to include the 80 meters. We mustn't forget that. So make a note of it. Underline it. So don't forget. So you can remember when you read the question, you've got it all sorted out. Okay. Now, let's go and let's see what we are given. We want to then find about maximum height of the ball. So let's say that the ball's initial position is over here. We know the position of that it's at that point, 0. It has, let's just take in line with that, make that a 0 point. It's at the bottom of the 9 meters. It's got an initial velocity of 12 meters per second. When it gets to its maximum height, we know the final velocity is going to be 0 meters per second. Okay, so let's write down all the information we're given, and we want to find the change in position, delta y. If you forget and put it as delta x, it's not going to matter too much. You're not going to get penalized, but it's preferable to write delta y, y being the vertical, x being the horizontal, just as a convention. We know the final velocity is 0. We know the initial velocity is 12 meters per second. And we know that the acceleration is equal to 9.8 meters per second downwards. Now look here, this was up and this was down. So put in the directions. Now we're going to decide direction. Let's make up as positive. So I'm going to say, for this part of the question, let's say direction. We're going to say up, positive. Next point. What equation are we going to use? Well, I haven't got time. I'm not given anything about time. But I do recognize that there is an equation that says V final squared is equal to V initial squared plus 2A, and that's delta Y. Okay, from the data sheet, no problem with that. Now guys, be very careful here. We've had some questions about substitution where people say, I don't get the right answer in the memo. I've tried it 100 times. There are two places that people make mistakes. They forget to square. I've done that. I know I've done that. In a previous show, I forgot to square. We make sure that we square. Second thing is make sure that you've got your directions right. So final velocity, we substitute 0 squared, 0. We're going to say the initial velocity was 12. Now, we've said up is positive, so it's 12 squared plus 2 times minus 9,8 times delta y. Now, it's just a case of doing some maths. In fact, at this point, you've got most of the marks that are allocated for the science. So what we're going to do is we're just going to solve this, and we're going to say that's minus 144. And we're now going to divide that by let's just get it on the calculator, 2 times 9,8, 2 times 9,8, and that's going to give us 19,6, 19,6, and be aware that that's also a negative, 19,6, and that will give me the answer to delta y. So what I'm going to do is I'm going to get that calculator back up again, and I'm going to substitute that value in, and that will give me my maximum height from where it was kicked. So the delta y is going to be, notice the minuses cancel out, so we know that it's not a negative, it's above the position, it's in the positive direction from its initial position, and we're going to say, right, let's get the calculator. It looks like my calculator's disappeared. But that's not a problem. We're just going to, need to just take a quick one here. I'll pull it up. Just in the meantime, will you just check, is there anything else on the page?
Yes,
while
there
we're waiting
actually
for that
is.
calculator?
There actually is, John. Do you want me to ask you?
Yeah, please do.
Okay, so there's been questions on lost volts.
Okay, that's fine.
I'm just telling you now, before you do this one, people have been asking what you mean by these lost volts, and how do we calculate it?
Okay, very good question. I know this is in the middle of this question.
Yeah.
Can we just...
Let's reserve that
let's
for
just do the
now.
calculation
Okay.
here, and I'll answer that straight away. 144 divided by 19,6, and we get the height from where he was kicking of 7,34. I'm going to round that up because 7,346, so I'm going to round it off to 7,35. Okay, so 7,35 meters. But guys, remember what I said in the beginning, that we must remember to add in the 80. So the maximum height above the ground, and I'm just there, is going to be 7,5 plus 80, 7,35 plus 80, which is going to be 87. Oh, what am I doing? 87,35. 87,35 meters. Okay, so that's the maximum height of the ball. Right, let's make sure that we've got vertical projectile motion sorted out. That was just for that ball going up. Now, I asked Kat to give us a question, lost volts. Let's just go back to that. I know this is jumping around, but remember we were talking about the EMF and the potential difference. Difference between an open switch and a closed switch. Over here where work was done. Do you remember that?
Yes, I remember
now,
that.
what happens is because this one is going to be less, the work done inside the battery, the work done between there and there, that is equal to the I times the internal resistance. And we call that V internal, and that's also known as lost volts.
Oh, okay.
Now, interesting that what we need to recognize. We need to recognize that's also equal to EMF minus V external. So if we take it, we recognize from the formula on the data sheet, V external plus V internal will equal EMF. I've just rewritten it in that form. Okay.
Yeah, I can see that.
Okay, guys, let's just move on because that was the first part of this question. And I want to just brief you on the second part, which I think is the more interesting one. So we know now that the ball gets to a maximum height of, look where Layla is. She's at 89 meters to start with. And the ball, if you got to my answer over here previously, was 87.35. So she started at 89. And we know that the ball gets to a position a couple of seconds later of 87, what was it? 87.35. Okay? 87.35. So we know that's there. But remember, this is a little bit while later. In the meantime, the balloon has got closer. The balloon has moved down. As the ball was moving up, the balloon was moving down. And the question is, will Layla be able to catch the ball in flight? We're asked to show all our calculations. Now, I think that's a superb question. How are we going to do it? I think you need to just take a few moments and see if you can work this out. Because if you think about it, it's got so much involved in it. So you've got that picture at the moment, the balloon at 89, the maximum height of the ball at 87, the balloon is moving downwards. Is Layla going to be able to catch the ball? Well, what do you think? You need to show your question. So it's not good enough to say, yes, Layla will catch the ball, or no, Layla won't catch the ball. Make sure you answer the question when you do your calculation. So you need to put one of those two answers, but you've got to show some calculations. So how are we going to do it? I think what we need to do is leave you with that question and give you a little bit of time, and I'll come back to it. In the meantime,
awesome. It'll be like a challenge.
It's a bit like a challenge question, yeah. In the meantime, are there any other short questions? Because we've got about a minute or so before our next break.
Okay, John. Remember you asked about momentum.
Yes.
There is one that Uwais asked. He asked, what's the difference between momentum, change in momentum, and impulse? He's confused at what the formula is.
Okay, excellent. Again, the learners are coming up with some brilliant questions.
They are such awesome questions.
They are really good. So let's go to that question. So the question was about?
It was about momentum, change in momentum, and impulse.
Momentum, and then we've got, I'm going to write change like that, delta P.
And many people were asking what P is. Now you guys know that P is momentum. I've written it up on the page in case you're confused. And John had said, don't ask why, it is just P. So you guys must listen out to what John says because he said that.
And this is change.
That's change, yes.
Change in momentum.
That's it.
Okay, so let's see if we can just shift that to that side and move that over. And now, let's define them. Momentum is simply the product of an object's mass and its velocity. Okay? So what we're going to write down here is we're going to say what P is. Momentum is the product of mass times velocity. The units that we use are kilograms, meters per second. Very simple. It is a vector. All of these are vectors. So make sure that they have direction with them. So we've got to make sure of that. Second point, change in momentum. Well, when we talk about change in science, what do? We think about change. We're going to say, what is the final position minus the initial position?
Yes.
Okay. So it's always final minus initial. Change in energy, final minus initial. Same thing here. We're going to say the final momentum minus the initial momentum. Okay. Simple. Put it out. Impulse. Now, here is the one that I like about impulse. Impulse is equal to, and we need to just make sure that we get this right. Impulse is force times time, okay? But that is equal to change in momentum. So here's something that I think you need to recognize, that those two are very close. They're in fact the same.
Yeah.
Okay? There are two ways of recognizing these. And when we do it with momentum like that, we can have units of kilogram meters per second. But actually, when we asked for impulse, notice what the units are here. It's Newton seconds. Very important that if you ask to work out impulse, it's Newton seconds. And there's one last thing, and I don't want to go away from this, because it's really important. Newton's second law was originally broken up from this observation. And that is, and you can have a statement of Newton's second law based on impulse. We can say the net force is equal to the rate of change of momentum. Okay, so that's another alternative for Newton's second law, and it's actually the way that Newton said it. If there's a change in momentum, there's got to be a force involved. If it happens over a certain time, the rate of change of momentum is the net force or the resultant force. Okay, Kat, I think
let's take a break.
Yeah.
Especially because you guys know
I've got the
that,
challenge question.
Yes, you guys know that there's a challenge after the break. So stay with us, guys. During the break, take your pen and a paper and quickly jot down what you need to jot down. Write the answer on the page, guys. Make sure that your answer's on the page. I will check it out. I will show John, and John will be going through it right after this very short break. See you now. Welcome back, Mindsetters. Wow, how fantastic you guys have been. The questions are streaming in and they are great. They show how much you guys are understanding and how much you're willing to even dig deeper into your understanding, which is actually so great. And I know you guys are very happy that John has managed to answer most of your questions. Of course, we're not here all day, so we can't do all of them. But remember that tomorrow, same time, same place, there is a live show. So make sure that you've prepared those questions, copy and paste them so that you can post them again tomorrow. Because tomorrow, who's on? Tracy and Tracy, and they'll be here to do them for you guys. So make sure that don't lose hope. Repost your questions. If perhaps you couldn't go through them today, make sure that tomorrow your question is answered. Make sure.
Can also email helpdesk@LearnExtra. And I'll make sure that Tracy and Tracy get those questions. So guys, that's the best way. If you've really got a question, make sure you email helpdesk@LearnExtra, and we'll make sure that that gets up. And we'll answer those, even if we don't answer them on the show.
Yeah.
I'll be working at those all the way through tomorrow. So I'm not at school tomorrow morning. I'm here making sure that we can give you the support that you've got. Okay.
Of course.
Right. So I set a challenge. Have we got any answers yet to this?
We don't have any answers yet, but can I tell you, Tandega asks, why aren't we adding 9 meters on the distance too, since it's above 80 meters?
Okay, very good question, but look at what the description is. The balloon is at 89 meters. The ball, so the balloon, we've added 80 plus 9 to get the balloon. The ball, we said it went up 7,35 plus the 80. So we know that that's not at the same time. This was the starting time. So let's just go back because I've skipped over. This was the starting position of the balloon. That was at the start. And what we need to recognize is this is at the end or at maximum height. We don't know when it was, but we're going to need to find that out. And so there we are. You know what, guys? I think you need to sweat on this one a little bit longer.
Yeah, I think so.
And even if we've got to answer it first thing tomorrow, we will do that. But I want to see you're working on this one.
Yeah,
and maybe we'll throw in something. for the person that gets it. Make an
It's
incentive.
it's one that looks very similar to the ones that come up in exams. Hey, John?
Absolutely, absolutely.
Yeah.
Okay, the reason I want to move on is lots of you have been asking about work energy, but I want to, before I answer this question from Intando, who's a regular contributor, and she's got I think she's got a study group going.
Yes,
that's on
yes.
on a page. So check that out as well. Great question, Mtando. We're coming to that now. But there was a short question before that, just a one-word quick explanation about Huygens principle. What's
Yes.
Huygens principle? So I'm going to just quickly give you an explanation of Huygens principle, because I can answer that quickly. Huygens, he was a Dutch physicist, and he said, when we're talking about waves, so this is about waves, he said, if you want to know what a wave is like, then you can think about them as forming wave fronts. So water waves in a pool, a set of ripples, they move across a tank like this. Or where a stone is dropped into a pond, you're going to get ripples that ripple outwards from where the stone is. And Huygens attempted to explain either the movement of waves like that, or like that, circular waves or straight waves, using this idea. He said, guys, if you want to find where the next wave front is, if you want to find where the next wave front, and I'm just going to do it, you could do it over here, you could do it over here as well, but I'm going to use it on the straight waves. Then what you've got to do is you've got to think about this wave front as being made up of lots and lots of little sources of waves. Okay? They're positions where waves are generated. And these generated waves are going to radiate little wavelets. So he reckoned that these are like stones dropping into the pond. And so I'm going to draw them in a lighter color. And he said, think about them as being little wavelets being produced from each of those sources. Now look what happens. If you do this accurately, and that was his point, he did it very accurately with the geometric, with rulers and protractors and all that sort of thing, accurate drawing. He said, if you've got this frequency right, then each of these would combine to constructively interfere and therefore generate the points of the new wave front. Where those intersected would form the line of the new wave front. So Huygens principle simply says that every point on a wave front can be treated like little particles that are producing new waves. This is particularly important in explaining the principle of diffraction, where if we've got a barrier in the way, so if this is a barrier, different color, then what's going to happen, we can explain why waves will bend around the barrier and they will radiate like that, because the waves at this point are acting as little sources to indicate movement in that direction. Okay, I know that was a little bit involved, but go and look at it in a textbook, go and look at it in our study notes. It is explained there as well. Okay, hope that's answered that question.
Yes,
but let's get back to Mtando's question now. I'm not sure whether I'm going to have time to answer it all, but so many people are worried about work energy and power and work energy on inclined planes. Guys, don't worry. Take it easy. Make sure that you stay tuned to the next sessions after this live show, because coming up straight after this, we're going to be looking at this morning's session, one that we started this morning, on vertical projectile motion and work energy theorem, work energy power. But I'm going to try and do as much of this as I can. What we don't do today, we'll try and finish off tomorrow. So very quickly, we've got the fact that a 3-meter block slides down at constant velocity of 7 meters per second. So this 3-meter block, 7 meters per second, it's going downwards. Sorry, it's not there. I've misread it. Read the question. As Ashraf would say, read the full question. And that's where it's sliding. It's sliding along there. So I'm going to make sure that I've got it right. It's going at 7 meters per second. It then says it's a horizontal surface. It then strikes rough ground, causing it to experience constant frictional force of 30 meters per second. The block slides 2 meters under the influence of this frictional force before it moves up a frictionless plane. So the frictional force over here is 0 newtons, and over here the frictional force was 30 newtons. Okay, so we've got that. It then says the block moves a distance of d up the ramp. So it moves up the ramp d before it comes to rest. Remember what rest means. Rest is its final velocity, and it's 0 meters per second. Show by calculation that the speed of the block at the bottom of the ramp, is 3 meters per second. Okay. Now, guys, we're not given anything about the height. We're told that it's a distance d, so we're not given that. We're pretty much stumped. We need to think about what we're going to do. And it looks to me that there's only one way to approach this, and I'm going to start by looking at this 2 meter section. So I can't deal with the last section. I'm going to deal with this section over here, and I'm going to say, I remember that if I can work out how much work was done, the total work done over here, then I know that the net work is equal to the change in kinetic energy. And that will help me a huge amount. So that's how I will do this particular question. I also know that net work, the work done in this section over here in the 2 meter, is equal to the force applied, or the net force, times the change in direction, a change in displacement, a change in position, times cos theta. Now, what are the forces that this block is experiencing in that rough section? So what forces is it experiencing? Over here, it was moving at constant velocity. If it was moving at constant velocity, we know that the net force is equal to 0 newtons. We also know that it was a frictionless surface, so there was no applied force. The object was moving, and it was moving at a constant velocity of 7 meters per second, and there was no other force attached to it. There was no force pushing it, no force pulling it. It gets to here, and the only force that's acting on it is 30 newtons. 30 newtons due to friction. Now, before I start the question, I'm going to say that the object, the direction for this part of the question, I'm going to say, let's make to the right positive. Okay, so if we're going to work out the net work done in this part, then what I'm going to do is I'm going to say to myself, what was the net force? Well, the net force I've just described to you is going to be equal to the frictional force, which we know was 30 newtons. But in which direction does friction act? Remember, if the object is moving to the right, friction always acts in the opposite direction. We've just said to the right is positive, so I'm going to make to the left negative. So it's negative 30. What about the change in position? Change in position, if you look at the question, change in position from the beginning of the rough to the bottom of the slope was 2 meters. Okay? Now what about cos theta? Cos theta is the one that people get confused about. In this case, what we've got to do is we've got to say the direction of the force was in that direction. The direction of the change in position was in that direction. They, I hope you can see, are not in the straight line. They are an angle apart. They are, in fact, 180 degrees apart. So when they're opposing each other, we can use 180 as the angle. So 180. Now, this is very important, because if you substitute in here now, what you're going to get is you're going to get 60. 30 times 2 is 60, but it was minus 30, so that's minus 60 times cos of 180. Cos of 180 is negative 1. Cos of 0 is 1. So over here, we're going to say that, I hope you can see, minus 60 times minus 1 is going to give us 60 Newton. Sorry, not 60 Newton. Remember, it's work, so it's joule. So that was the newtons, this is the joules, 60 joules. Now, guys, I'm having to speed through this. What we're now going to do is we're going to apply the work energy theorem. We're going to say, we recognize we want to find the velocity at the bottom of the slope. So we're going to say the net work, which we've just calculated, is going to be the change in kinetic energy final minus kinetic energy initial. And this is just for the flat part. Remember, it's half mv final squared. Look out for the square. Minus half mv initial squared. And we can now substitute. So we've got this as being 60 joules is equal to half the mass of the object. Let's see, 3 kilograms, and it was moving at 7. So 3 kilograms, v final squared, minus half 3, and the initial velocity was 7, and we must square that. I think I've got that all right. Check. Yes, 3, 7, got it. So now we just have to work this out. And we get 1.5 v final squared minus 1.5 times 49's, 1.5 times 49, because we know that, where's my calculator now? I think it's that one. Let's get it. Just move it over. Let's do 0.5 times 3 times 7 squared. Don't forget the square. And that equals 73,5. 73,5. So we put that in here, 73,5. Now, I hope you can see that we can then do a little manipulation, and we're going to get v final squared is equal to 60 plus 73,5 divided by 1.5. Okay, that 1.5 didn't look very good there. So 73,5 divided by 1,5. And let's use the calculator, not that one. Let's use that one. And that was my one answer. So I'm just going to add it plus the 60, which was there. So I'm going to say 60 equals divided by 1,5. And notice that that should be v squared. I'm forgetting my squares again. That should be v squared. So we've got a square over there, and we've got that 89. We've got 89 is equal to v squared. So here we go, equals 89. So what is v going to be? Can you guess? Square root of 89 is what we're going to need to do. So we're going to say answer square root, or square root answer. Where's the square root? There, square root answer equals that. And let's get it. 9,443. Now that doesn't look right to me because it should be slowing down. I might have made a little mistake somewhere. Let me quickly just check. Kat, can you just mention if there are any other questions?
There are no other questions now relevant to what you're doing, John, but then what's important is that you guys have been saying on the page how you're really excited for this exam because you're starting to understand more. That's what's awesome, is that when you understand more, you realize that you can be excited for your exam. You don't have to be nervous and scared about it because you already have it covered. You basically have all you need in the box, guys. What I can say to you guys is that once you study really, really hard, once you really sit down on the ground and you're actually absorbing what you're studying, you have the potential to do extremely well. So what John is doing now is so important because this teaches you some techniques that you can use in the exam that will make sure that you don't fail and you don't get left behind.
Thanks, Kat. Now, guys, I know that we've only got a few seconds left of this particular show. When you strike out like this, and I've realized that I've got an answer, and the reason that I realized that it's wrong is because I started with 7, okay? So let's be clear about this. I started with 7 and I'm applying a negative force. It should be decreasing. So this answer here must be less. When I've done my calculation and it's just a slip somewhere, I recognize that that is bigger than 7. It must, the square root of that is going to be a number bigger. So there's a mistake somewhere here. So I'm going to have to go back and I will post the correct answer onto the page. I'll work it through, but we don't have time to do it directly now. Okay? But I hope you've got the method. The method's the important thing. The arithmetic's not that essential, because I know that you're going to get different numbers. You're going to be able to use your calculator, and you've got time to do it as well in the exam. But important learning points that you need to do, you need to pick up from me here, is that when you see an answer, check and say to yourself, is this reasonable? Is it right? Is the physics correct? I know the physics is wrong here. Okay, but I want to just move on from there and just explain the next part of the question, because I think this is probably a definite question that you're going to get in the exam on Thursday. It's more than likely that you'll get one like this. So the next part of the question says to us, draw a free body diagram, okay? Draw a free body diagram to show all the forces acting on the block in a direction parallel.
John. Okay, you can have 10 seconds
10
to finish
seconds,
this
quickly. So if there is that, there's no friction, so the only force parallel is that way, down.
Oh, okay.
So it's the force of gravity parallel to the surface. That's it.
Thank you, John. You know, time goes extremely fast, guys, but don't worry at all, because there's a show tomorrow. And of course, John will be posting exactly what you guys need for this question. In the meantime, it'll help you if you do it yourselves. And don't forget that John had given you another challenge to finish. So make sure that you post that, guys. Make sure that you're on your best game for your exam. From me, good luck, guys. I know that you guys can do fantastically well. Thank you. Bye, guys.